Hello one and all, welcome to another online video by Einstein Academy. In the last video, we look at learning outcomes H and I from the topic of chemical bonding from the GCH2 chemistry syllabus. In this lecture, we are going to look at some past year A-level questions that specifically test on these two learning outcomes from chemical bonding. So these are the two learning outcomes. It's basically the intermolecular forces of attraction. I remind you again, there is ID-ID forces of attraction, PD-ID forces of attraction, PD-PD forces of attraction, as well as hydrogen bonding. And also to be able to outline the importance of hydrogen bonding to the physical properties of substances, including ice and water. Okay, so let's begin looking at past year A-level questions that test on these two learning outcomes. So November 2007, paper 1, question 18. The gecko, a small lizard, can climb up a smooth glass window. The gecko has millions of microscopic hairs on its toes, and each hair has thousands of pads at its tip. The result is that the molecules in the pads are extremely close to the glass surface on which the gecko is climbing. What is the attraction between the gecko's toe pads and the glass surface? And these are the four options: coordinate bonds, covalent bonds, ionic bonds, and van der Waals forces of attraction. Now, like coordinate bonds are like covalent bonds really. And so these two answers is like very similar. And ionic bonds, so among these three, right, these are very strong forces of attraction, right? Because coordinate bonds are covalent bonds, which is attraction between the nucleus and the shared pair of electrons, which involves full pluses and full minuses. And covalent bonds is the same thing. Ionic bonds is also between full pluses and full minuses. Whereas for van der Waals forces of attraction, which is another term for intermolecular forces of attraction, is between partial pluses and partial minus, which is like weaker. Now, if the attraction between the gecko's toe pads and the glass surface is this three type of bonds, right, then once it forms, it's not going to be able to break easily, and hence the gecko will just be stuck to the glass surface and not going to be easily moving up the glass surface. I can also tell you that, like for glass, right, like for example, if you have a piece of glass, they are actually made out of many OH groups that is coming out of the glass. Okay, so I can also tell you that basically it is very likely that the attraction between the gecko's toe pads and the glass surface is through that of hydrogen bonding, which is a type of van der Waals forces of attraction. November 2012, paper 1, question 5. The boiling point of water is greater than that of HF 100 degrees Celsius as compared to 20 degrees Celsius. Which statement is the correct explanation of this? Okay, so option A, each hydrogen bond formed between water molecules is stronger than that formed between HF molecule. If you were to look at the water molecule, right, so the oxygen is more electronegative than the hydrogen. And then if you compare that, okay, so as in, I mean, the hydrogen bonding between water and water will be like this. Whereas the attraction between HF and another HF would be like this. Okay, however, right, because fluorine is more electronegative than hydrogen, right, so it is expected that the magnitude of this delta minus and this delta plus to be stronger than this delta minus and delta plus in the case of water. So it is expected that actually the hydrogen bond in HF would actually be stronger than that of water molecule, and this is opposite to the thing mentioned in option A. So option A is not the correct answer. There are more atoms in the water molecule than there are in the HF molecule, so van der Waals forces of attraction is stronger in water. So this van der Waals forces of attraction usually refers to ID-ID interactions. So again, right, I remind you the two factors that determine the ID-ID forces of interaction is the polarizability of a molecule, which basically depends on the number of electrons in the molecule. It doesn't depend on the number of atoms, because like if you have a molecule that has many hydrogens, right, and hydrogen only has one electron, it will not have a lot of electrons, and the instantaneous dipole effect will actually not be that great. It is actually the number of electrons that is important in deciding how strong the ID-ID interactions are, and not the number of atoms. Okay, so this is also not an correct answer. It's not based on the number of atoms, but on the number of electrons. Okay, option C is the correct answer, so let me skip that for a while and let's talk about why option D is wrong. The water molecule has a greater permanent dipole than HF molecule, so as we mentioned, fluorine is more electronegative than hydrogen, so the delta plus and delta minus created in HF would actually be stronger than that in water. So actually, the water molecule actually has a weaker permanent dipole than the HF molecule, and option D is wrong, and C would thus be the answer. So if you were to look at the water molecule, right, this hydrogen can form a hydrogen bonding with another water molecule. So on average, right, the water molecule has two hydrogens and one oxygen, and moreover, right, this oxygen actually has two lone pair of electrons. So actually the number of hydrogen bonding that water can actually form between water molecules will actually be greater than that of the HF molecule, since HF only has one hydrogen, although it has another three lone pairs, right? But it is still true that the number of hydrogen bonds that water can form between between different water molecules will be on average greater, and that's the reason why, since there are more hydrogen bonds between water molecules, we actually have to break a greater amount of hydrogen bonds between water molecules in order to boil the water. And that's the reason why water has a higher boiling point as compared to HF. November 2014, paper 1, question 4, water methanol and methoxymethane, CH3O, CH3, have similar shaped molecules, so this three. What is the strongest intermolecular force in water, methanol, and methoxymethane? So why do they use the word strongest intermolecular force in water, methanol, and methoxymethane, right? The reason is, I've already mentioned to you, right? Every molecule that's covalent in nature will always have ID-ID interactions because of the fact that electrons that's not involved in bonding are still on average evenly distributed within the whole molecule, and by chance they can congregate on one side and create an instantaneous dipole, and when the instantaneous dipole approaches another molecule, it can induce a dipole in the other molecule. So ID-ID interactions is present in all covalent molecules, but it's the weakest. Okay, so but we are interested in what is the strongest intermolecular force of attraction. So basically, are there any other interactions that is stronger than the induced dipole that is present within these three molecules? So for the case of water, we have a H bonded to O, and therefore this is immediately hydrogen bonding. Okay, this is the same case, we have a H bonded to O. So anyway, if this approaches another water molecule, right, this attraction would be the hydrogen bonding. And if this approaches another methoxymethane molecule, another methanol molecule, it would also interact through hydrogen bonding. Okay, so this is also hydrogen bonds. Whereas for this molecule, there is no H bonded to F, O, or N, although there's an O and there's a H, right? But the H is not directly bonded to O. Okay, then like we have to decide whether it's PD-PD or ID-ID interactions. And for that, we draw the shape of the molecule using VSEPR theory. So the shape will be bent because there's 4 electron domains and there is 2 lone pairs of electrons, so it's bent. And oxygen is more electronegative than carbon, so we would draw 2 bond dipoles. When we add these 2 vectors, we will get one that overall points in this direction, and hence this molecule has a net dipole moment. And since it has a net dipole moment, the type of interactions between a methoxymethane molecule and another methoxymethane molecule will be that of PD-PD interactions. And hence, this is PD-PD interactions, this is hydrogen bonds, and this is hydrogen bonds, and the answer would be option A. Okay, the last question, the November 2009, paper 3, question 4b, part 1. The molecules of ammonia and methane contain the same number of electrons. So if they contain the same number of electrons, it's telling you that basically the ammonia and the methane have very, very similar strength of ID-ID interactions, and that will not be a factor that will be compared in order to determine the overall intermolecular force of attraction between ammonia and ammonia, as well as between methane and methane. Okay. However, and they also have approximately the same size and mass, so it's the ID-ID interactions is irrelevant to the answering of this question. However, their boiling points differ widely, and you can see that methane, the boiling point is -164, whereas for ammonia, the boiling point is -33. Okay, so just an explanation for the difference in boiling points. So since ID-ID interactions is not valid, so anyway CH4, right? The molecule, it's tetrahedral in nature. There are no polar bonds. So this is only ID interactions. Whereas for ammonia, there's a H bonded to N, right? And hence this actually operates through hydrogen bond. Okay, so the way you answer the question is that since NH3, the type of interactions between NH3 and NH3 is through hydrogen bonding, which is much, much stronger than the ID-ID interactions between methane molecules. Hence, a greater amount of energy is required to break the hydrogen bonding between ammonia molecules, and hence ammonia has a much higher boiling point as compared to that of methane. Okay, I hope that having gone through these questions, you are now more confident in applying the concepts that we learned in the previous lecture to the answering of questions that is addressed to these 2 learning outcomes. As always, if you have any questions, just drop it in the comment section. I'll be more than happy to answer them. And I'll see you again for upcoming lectures on the next few learning outcomes from the topic of chemical bonding. Thanks for tuning in and see you once again.